In this video, we're going to learn about electron configurations. Now, previously, we learned about orbital diagrams as a way to express how electrons are distributed in an atom. And so, for example, for oxygen, which has 8 electrons, we would put 2 in the 1s, 2 in the 2s, and then 4 in the 2p, and the orbital diagram would look like this. Now, another way of expressing the way electrons are distributed in an atom is to use the electron configuration. And for oxygen, we would say it is 1s2, 2s2, 2p4. And what that means is that in the 1s subshell, there are 2 electrons. In the 2s subshell, there are 2 electrons. And in the 2p subshell, there are 4 electrons. Those things that look like exponents are just the number of electrons in a subshell that's indicated by the 2p, the 2s, and the 1s. And if we look back here, it's exactly the same thing that's being stated. Now, if you found it tricky memorizing the order in which subshells are filled according to an orbital diagram, the periodic table actually is organized to make it easier for you to tell. So if we look, we've got what's called the S block over here. That's groups 1 and 2. We've got the P block over here. We've got the D block here. And we also have the F block down here. Now, if you look at the period number, period 1, period 2, 3, 4, 5, 6, and 7, the period number corresponds with the S and the P that are being filled. So in the second period, you can see the 2S and the 2P are filled. In the third period, we have the 3S and the 3P that are being filled. In the case of the D block, it's always the period number -1 that we're dealing with. So I'm going to write a little n-1 here as a reminder. And we can see, for example, that in the fourth period, yes, we have the 4s and the 4p that are filled, but it's the 3d, not the 4d that's filled. The 4d actually comes in the fifth period, the 5d in the sixth, and so on and so forth. Now, with regard to the F block, we can see that elements 57, 58, 59, they actually come after the 6s. So if you look in the sixth period, it actually is after the 6s where the 4f is being filled. So we're going to say that for the F block, we're dealing with n-2. So next, we'll sort of see how we can use location on the periodic table to figure out where we're stopping. And an example of this would be in the case of, say, vanadium. So with vanadium, which is element number 23, I look to where it is in the periodic table. I know we're in the fourth period and in the D block, so this is going to be the 3D that's being filled. And I know also that we are in the third element over. So the last term for vanadium is going to be 3D. And then from there, we just build up from the beginning. So we start with the 1s, which can fill with 2 electrons. And I can really look at it like elements 1 and 2, hydrogen and helium. They're both 1s. Then we go elements 3 and 4, lithium, beryllium. That's filling up the 2s with 2 electrons. Then we continue on to elements 5 through 10. That's over in the 2p, which can get filled with 6 electrons. Note that the 6 electrons signified by the 6 columns in this block. Then we go over to the 3s, which we fill with 2 electrons, the 3p, which we fill with 6, and then the 4s, which we fill with 2 electrons, and then that leaves us with our 3d3. Now, a good way to check yourself on this is to just add up all the electrons, and my 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 3 does give us the 23 that we're expecting. I would like to move on to the concept of what's called the noble gas configuration, which is an abbreviation. As you might imagine, if I wanted to do the electron configuration of, say, yttrium, that would be difficult. I'd have to go 1s, 2s, 2p, 3s, 3p, etc., etc. It'd be quite a bit. But what I can do is I can actually abbreviate many of the electrons using a noble gas, which is a group 18 element. These are my noble gases. And so, for example, if I am doing yttrium, element number 39, what I can say is that we have the nearest previous noble gas, which is krypton. Notice that before 39, the nearest of these group 8 elements is number 36. And again, it has to be the nearest previous noble gas. So even if you had iodine at 53, you'd be using krypton as your base. But we would say that for yttrium, we'd have Kr, and then after krypton comes 5s2, 4d1. And if you add them up, 36 plus 2 plus 1 does give us the 39 that we're expecting. Note that we're in the 4d, we're the first element there, and that explains why we have 4d1 at the end of our configuration. A couple things that come up sometimes is that students might notice that it looks like there's a little bit of a hole here. For clarity, a D subshell always holds up to 10 electrons, an F always holds up to 14, a P holds up to 6, and an S holds up to 2. 2, 6, 10, 14, you're always adding 4. That's the trend, that's the pattern here. Also, students may sometimes notice that we've got this weird thing where lanthanum and actinium are showing up as D block, yet they're also positioned in the F block. And well, remember this. There are holes here for lanthanum and actinium, and truly, lanthanum is an element that ends in 5d1, and actinium ends in 6d1. But the reason why they're showing up down here is the F block is kind of weird. Actually, the F electrons usually are filling in before the Ds. So if we had promethium, for example, we could say the noble gas before promethium is xenon, which is 54. So I'd say Xe, and then I'd say 6s2. And after the 6s does come the 4f. And promethium is 1, 2, 3, 4, 5 over into the 4f, so its configuration would end in actually 6s2, 4f5. That's the reason why lanthanum has to be here, because if you're counting cerium, you'd expect to be F2, praseodymium 4f3, neodymium 4f4, promethium 4f5, samarium 4f6, 7, 8, 9, 10, 11, 12, 13, 14. Interestingly enough, lutetium is actually going to be xenon 6s2, 4, 4f14, 5d1. Never write f15. It can't possibly be the case. And so that covers kind of the ends of your F block, which I understand is a little bit weird. Always go by the guiding principle that your F can fit up to 14 electrons, and if you're counting across the F block, you have to include 57 or 89 as your first element in the F block to get over to the correct number for, say, holmium or erbium or any of those. So I hope this video has been helpful. Feel free to leave any questions or comments in the comments section below, and thanks for watching.